Welcome everybody. I'm not gonna give you some long introductory remarks. I think we should get right to it. So this morning we're very lucky to have Pieter Blue from Edinburgh, who'll be talking about the linear stability of the Kerr spacetime in the outgoing radiation gauge. Pieter, take it away.
All right, thanks for the opportunity to speak. First of all, I'd like to, particularly as the first speaker, thank the organizers, particularly with the changing COVID situation. I'm sure it's been very difficult to organize this and make it happen. It's a lot of work to make these meetings work, and I'm very grateful. All right, so today I'm going to speak about some joint work with Lars Anderson, Thomas Bachtel, and Xiuan Ma. It's inspired by the question of black hole stability, and it's based on two papers, one from a preprint from 2019, Stability for Linearized Gravity on the Kerr Spacetime, and then a more recent one from last year, Nonlinear Radiation Gauge for Kerr Spacetime. So these are both from the archive. Let me start with some very basic things. It's the first talk, and the Einstein equations are beautiful, so I might as well put them up here to begin with. As we all know, it's the Ricci curvature minus 1/2 the scalar curvature times the metric is equal to 0. I'm going to say some things on this slide that I'm sure are very familiar to lots of people, but I just want to set the scene for some of the points I'm going to make later. This is very beautiful from a geometric point of view, but from an analytic point of view, it can be difficult to deal with because of what you might call diffeomorphism or coordinate or gauge invariance. If you have an initial slab, some chart, initially you might have two solutions that are have a solution that is the same, but if you change the coordinate chart in some region, say in the future, then that will make it look different in the new coordinate system. And so you have a failure of uniqueness as a solution of a PDE. So the way that one resolves this is to impose gauge conditions. These are, one can think of as conditions on the coordinates. And by basic function counting, there should be 4 of these to append to the Einstein equation in 1+3 dimensions. So the vacuum Einstein equation plus suitable gauge conditions, and there's multiple choices of these, together, these form a well-posed evolution PDE system, for example, from the work of Choquet-Broha in the 1950s. And this system is, I'm going to say, essentially hyperbolic. One poses initial data and evolves it into the future. It has finite speed of propagation and so forth. But depending on the gauge, it might genuinely be hyperbolic, or it might be a coupled elliptic hyperbolic system. So that's not inherent to the Einstein equation. That has some part of it dependent on the choice of coordinates. So then the Kerr family of spacetimes is a very important object in general relativity. It's a 2-parameter family of solutions. There's a mass parameter m and a rotational parameter a. The famous Schwarzschild spacetime corresponds to when a equals 0, and Minkowski space corresponds to when m is equal to 0. For a less than or equal to m, which is the only case I'm going to consider today, this gives a black hole. There's many different coordinate systems that one could use. The one, I'm not going to really get into the coordinate expressions in this talk for the most part, but the one that is useful for this talk is the analog of the Eddington-Finkelstein coordinates that one has in Schwarzschild, where you have the level sets of a null coordinate v, r coordinates, which in Schwarzschild give the radius of the spheres and are more sort of just constructed in a convenient way rather than an inherently geometric way for the most part for a radial variable, and then angular coordinates, which are the standard spherical coordinates in Schwarzschild and a perturbation thereof in Kerr when a is not equal to 0. And the region that we're mainly interested in for this talk is the exterior of the black hole, where r is greater than this value m plus square root m squared minus a squared. So the space-time has two natural symmetries. It has a time translation symmetry running up the level sets of R and keeping the angular coordinates fixed, and in axial symmetry rotating in the phi coordinate. I should have also said that because the V level sets are well, they're in Schwarzschild, the level sets are null hypersurfaces. In Kerr, they're no longer null hypersurfaces, but the partial derivative with respect to R, that coordinate vector field, remains a null vector field. So if you think about in 3 dimensions x, y, and t, if you think about the yt plane, d by dt plus d by dy, that is a null vector field. It sweeps out that plane, but that plane is still a time-like plane, not a null plane. So it's that's sort of what's happening here for a not equal to 0. These particular vector fields, partial r, that are tangent to the V level sets are null, but they are not themselves, but the level sets are not null hypersurfaces. There's another couple of geometric features of the Kerr spacetime that are quite notable. The symmetries are generated by Killing vector fields. These satisfy that the symmetric covariant derivative is equal to 0, and there's a generalization of that in Kerr, a Killing 2 tensor, which is sometimes called a hidden symmetry, which is a symmetric 2 tensor whose symmetric covariant derivative is equal to 0. Another special geometric feature of the Kerr spacetime is that it's got algebraically special principal null vectors. Principal null vectors are quite difficult to explain, I think, in a sort of obvious geometric way. There's some multilinear eigenvalue problem for the Riemann curvature on any space-time. This gives you 4 null directions, and if these 4 null directions coincide with each other, then you have an algebraically special space-time, and there's a preferred choice of outgoing null vector and ingoing null vector, both of which are repeated principal null vectors in the Kerr space-time. So that makes the Kerr space-time algebraically special. And in the choice of coordinates that I've made here, the ingoing principal null vector is just minus partial r. And these are not merely null vectors, but they sweep out null geodesics, which is going to be an important property that we come back to later. All right, so the main motivating problem for this work is the Kerr black hole stability conjecture, which I'll state quite informally, that the exterior region of the Kerr family of solutions is stable under the evolution given by the Einstein equation. We have an initial value problem. If you take initial value for the Kerr black hole, you don't want to look at just the exterior. You want to have something that extends a little bit into the interior. You can then evolve that forward into the future. You would hope that that's going to have a maximal globally hyperbolic development, and one hopes that it has a complete null infinity. That's going to have a past. The complement of that is the black hole, and one hopes that if you take hyperboloidal foliation or some other sort of foliation that goes up to the end of null infinity, up towards time-like infinity, then the metric as you go that way should converge to a Kerr space-time, but typically not the Kerr space-time that you started with. All right, so there's been a lot of work on this problem for a long time. I'm going to start with what I call the perturbation theory of the so-called golden age, particularly the 1970s, where a lot of work in the physics community was done on this. But the study of stability of black holes is quite a bit older than that. It started with Reggie and Wheeler in 1957. And sort of looking back on it now, the way that I would look at it is that the Riemann curvature in 1 + 3 dimensions has 10 components. These can be combined into 5 pairs of, let's say, complex components, and these have a natural ordering on them, which have spin weights from -2 up to 2, and there's a middle component which satisfies a wave-like equation with a real potential when you perturb around Schwarzschild, and that gives the famous Reggie-Wheeler equation. So that was the sort of one of the first major results on stability of black holes. And then it sort of remained stuck there for 15 years. And then in the intervening period, the Kerr spacetime was discovered. And then Teukolsky looked at the stability of that and found that the extreme 2 curvature components, those with spin -2 and +2, satisfy a wave equation, but not a standard wave equation. It's both tensorial. It's not a scalar. It's got some sort of spinorial geometric structure to it. But more importantly, for this purpose, it's got both damping and anti-damping in different regions. And the anti-damping makes it very difficult to treat in the way that one would normally treat wave equations. So a year later than that, 2 groups, Teukolsky Press and Starobinski Churlov, found some other relations, which are now called the Teukolsky Starobinski relations, that relate the 2 extreme components to each other. And a year after that, Chrzanowski, you'll have to excuse my pronunciation, introduced a what you might call linearized gauge called the ingoing radiation gauge or the outgoing radiation gauge, depending on whether it's based on the outgoing or the ingoing principal null vector, and use this to reconstruct all the metric and connection coefficients from the 2 Teukolsky variables, the extreme curvature components. And something that has turned out to be useful is that Chandra noticed that, at least in the Schwarzschild case, there is a transformation that can be made between the Teukolsky solutions for the extreme components and the Reggie-Wheeler solutions for the middle component. So that's sort of the background. It laid out a lot of what the equations were, but it didn't really give any results on analysis of what the solutions looked like. The first result on the nature of the solutions was in 1989 by Whiting, and he showed that there were no exponentially growing modes in the sub-extremal case for the Teukolsky equation. This was a problem that I think a lot of people had thought about, and the fact that it took over 15 years to get even a result this week showed how difficult the problem was. And then very little about stability of black holes was developed for another 25 years or so. Of course, the stability of Minkowski was developed in this intervening period, which really advanced our understanding of the Einstein equation and nonlinear wave equations. But in terms of the direct problem that I'm discussing today, the stability of black holes, not much was known, I would say, in terms of like the actual perturbations themselves. Models with the wave equation and so forth were studied, but in terms of linear or nonlinear problems for black holes, there was sort of this 25-year period where progress couldn't be made. Shortly afterwards, there were a couple groups that made really big breakthroughs in my mind. In 2017, Ma and De Firmus-Holzapfel-Rodniansky independently found that there were energy bounds and Morowitz estimates, and De Firmus-Holzapfel-Rodniansky extended this to time decay for solutions of the Teukolsky equation. And this was a major breakthrough because the anti-damping, which sort of leads to exponential growth, what one might worry about, or some other sort of growth where things are competing with each other, was shown not to occur. this was sort of what was expected, but these equations were developed in the early 70s, and it took many decades to reach even these results. So this was a very major step forward. And last year, Elena Georgi converted these arguments from sort of Fourier type arguments with separation of variables and so forth, and put it in terms of purely physical space arguments using just differential operators, rather than looking at the Fourier modes. And so I think that's going to be a big step forward for going to the nonlinear problem. In terms of results on decay from metric perturbations, there was some work on Schwarzschild, and then that has more recently come to Kerr. So I'm going to try and summarize some of the work by various people, including some people in the room. So I hope I don't misstate anyone's result or offend anyone. There's a lot of very interesting work here, and I'm not always on top of all of it, but this is as best I understand it. So in 2016, de Firmus, Holzgel, and Rodniansky, in the Schwarzschild case, investigated the linearization of the Einstein equation in the double null gauge via first the Teukolsky equation. Then to analyze that, they sort of used the Chandrasekhar transform, and then were able to reconstruct the full metric from the extreme scalars, the Teukolsky variables. At about the same time, Hung-Keller and Hung-Keller-Wang also looked at the stability of Schwarzschild, but using the Reggie-Wheeler gauge. In quite a different approach, Hintz-Vagi and Hintz, for very slowly rotating black holes with a cosmological constant, proved stability. And this is quite a different sort of result. In the one sense, it's weaker because the de Sitter result, the de Sitter cosmological spacetime means that you have exponential decay rather than polynomial decay, which makes the nonlinear estimates easier to do, and the decay estimates much stronger. On the other hand, compared to a lot of the other things on this slide, it's a fully nonlinear result instead of merely a linear result. So in some ways it's weaker, but in some ways it's stronger. In 2018, Johnson returned to the Schwarzschild stability, reinterpreting the Reggie-Wheeler gauge as some sort of inhomogeneous wave gauge. So that sort of put a new way of looking at the Reggie-Wheeler gauge, which I think was interesting. So then the work that I wanted to talk a little bit about today, but I'm going to mainly focus on the gauge, was that based on the known results for linearized Einstein equation for the Teukolsky equation, we were able to reconstruct all the metric coefficients using Chrzanowski's outgoing radiation gauge, and that allowed us to prove the linear stability of very slowly rotating Kerr spacetimes. And about the same time, Hafner, Hintz, and Vagi proved a similar result using an inhomogeneous wave gauge. More recently, last year, Kleineman and Scheftel have a very long, I think 800 pages or so, paper on the nonlinear stability of the Kerr. So not just linear, but the full nonlinear stability of the Kerr solution, assuming there's estimates on the nonlinear Teukolsky equation, as I understand it. So this is sort of a similar, I mean, obviously it's a stronger result because it's a nonlinear result, but it's a sort of similar strategy to what we were considering in some ways, in that it takes the Teukolsky equations and tries to solve those first, and then from that reconstruct everything else and get the decay estimates for them. But obviously that's a major step forward, since it's a nonlinear result rather than just a linear one, which I'm speaking about. All right, so that's the background. And as you can see from this, there's various different gauges that people have used. And so now I want to speak a little bit about what is a linearized gauge. So I'm going to assume we have a solution to the Einstein equation. I'm going to assume that there's a linearized metric H. And in discussing this, I find it helpful to do a comparison with the Maxwell equation, which is a linearized linear geometric equation that we usually have more intuition about. So we could ask, what does it mean to impose a linear gauge? And one answer you might give to this is that it is an equation satisfied by the linearized metric H. So in analogy with the Maxwell equation, the temporal gauge is that the zeroth component is equal to 0. Another concept that you might use to define a linearized gauge is to say that if you have the original metric perturbation H, you want to be able to do a linearized transformation of the metric, which is that you have a vector field X and you lead drag the metric with respect to that vector field X and take the derivative to get a new linearized metric H prime. And so it's not merely that you have conditions on that you want the linearized quantity to satisfy. You actually have a process for going from one linearized quantity to a new linearized quantity. And so, for example, with the temporal gauge, there's an explicit formula you can take. So if someone gives you a metric in, a vector potential in their gauge, you can convert it into the temporal gauge. Another definition that you might take for a linearized gauge is that you have an actual gauge for the nonlinear equations themselves, and you're doing a linearization around that. So these are three sort of related ideas, and I think the best of these is the third, and certainly if you're trying to advance towards understanding the nonlinear problem, the third is the one that one would need to take, that you would have some nonlinear system, you linearize it, and then analyze that resulting linearized system, rather than, which is what was happening sort of in the 70s, that you take the ungauged equations, linearize them, and then try to put extra conditions on them. So there's a question of whether you impose the gauge before the linearization, and that is the better way of doing it, particularly if you want to get to the nonlinear problem. So then even at the nonlinear level, you can ask about what does it mean to impose a gauge, and you can sort of have the same three things again. You could have an equation that you want the metric to satisfy. You could ask that there really is a family of diffeomorphisms, so that if someone else gives you a metric that isn't in your gauge, you have a way of transforming it into your gauge. And you might further want that once you've gotten it into your gauge, that the Einstein equation is actually well posed in that gauge. So again, this final view is probably the one that's going to be most productive for going to the nonlinear problem, that you want to have a version of the Einstein equations with a gauge that gives you a well-posed initial value problem that you can solve. That's the ultimate goal. Then you get a model problem from that by linearizing that system. All right. So let's review what Chrzanowski's outgoing radiation gauge, which is what we used in our linear stability result, was. It consists of several pieces. You have the background metric, you have the ingoing principal null vector, and you have some linearized metric H. So we're slightly changing the notation that he used and the terminology, but this is sort of cleans it up a little bit. It satisfies the linear outgoing radiation gauge if the linear metric contracted with the ingoing principal null vector is equal to 0. So that means all the ingoing components are set to 0, and that's why it's called the outgoing radiation gauge. And we contract over the betas, so we have one free index alpha here, and so that gives us 4 equations, which is sort of the right number of equations that we should be expecting. It's said to satisfy the linear trace condition if the contraction of the linear metric with the background metric is equal to 0. And it satisfies Chrzanowski's outgoing radiation gauge if it satisfies both the outgoing radiation gauge and the trace condition. And this might make you nervous in that we already had the right number of equations here, 4, and then there's an additional one here. And so we've now got a total of 5. So there are some advantages and some disadvantages. The advantage is that you get a hierarchy of transport equations that allow you to descend from the Teukolsky equation to all the other components, in particular to descend from the Teukolsky variables to the non-vanishing components of the linearized metric. The disadvantage is that it seems that there's too many equations. All right. So Price, Shankar, Whiting in 2006 found a good resolution to this. And so one way of thinking about that, in the 3 ways I had of looking at the linearized gauge conditions, what Chrzanowski was doing was the first of those, just imposing a condition. So what Price, Shankar, and Whiting did was that they introduced a vector field so that if you have a linear metric h, you can construct a new linearized metric h plus the Lie derivative. And when they investigated this, they found that the condition that the new metric satisfies the linear outgoing radiation gauge is equivalent to a system of linear transport equations for the vector field x. So you can solve that in terms of several free variables. They also found that if on the initial data, the trace condition is satisfied, then that trace condition is propagated into the future and is also satisfied. And this sort of gets around the mismatch in the counting. The outgoing radiation gauge, those 4 conditions are imposed in the space-time, but you still have a residual gauge condition that you can apply on the initial hypersurface. So the initial data can be linearly re-gauged so that it satisfies the trace condition, and then that propagates into the future and the past. So then you get it everywhere. And so you're using this residual gauge freedom that one can impose on the initial data to get that 5th condition. So in particular, they could choose a vector field x so that the transformed linear solution satisfies all 5 of Chrzanowski's outgoing radiation gauge condition. All right, so we wanted to extend this to nonlinear problems. So we have our background metric, mg, g ring, which is the reference. We have the ingoing principal null vector, which for concreteness is the one with respect to the background metric. We're not going to look at the whole manifold. We're just going to look on a sort of a subset. And then we have some perturbed metric G. So G is the perturbed metric, G ring is the background. And so we say that the metric G satisfies the nonlinear outgoing radiation gauge if the difference between the foreground and background metrics, when contracted on that ingoing null vector, is equal to 0. So it's basically just sort of the obvious nonlinear version of the linear radiation gauge. And then we do the same thing with the trace condition, that we take the difference between the foreground and background metric, we contract it against the background metric, and we want that to be 0. And that's our nonlinear trace condition.
Peter, can I ask a question?
Please.
So I don't understand condition 2. I mean, do you have a system of coordinates for the nonlinear and the linear metric at the same time so you can compare?
Right, yeah. So if you think about tensor fields on the manifold, then everything written here is well defined just purely geometrically, right? That you have the tensor field G and you have the tensor field G ring, and you take their difference as tensor fields, and then you contract that against the background tensor field, and that's purely at the, you know, in the way that I've described
Abstract,
it, that's purely
in an abstract sense.
in an abstract sense, but you're still free to apply diffeomorphisms on G, right? And that's what's going to be coming up in a slide or two, that we could apply a diffeomorphism on G to sort of have the same perturbation, but better by applying the diffeomorphism freedom. Does that sort of answer your question?
A little bit, yeah. Well,
Yeah, okay.
anyway, go on.
All right. Thanks for the question. And if anyone else has questions, yeah, please do ask. So I wanted to say a little bit about this business with the open sets, because it's a little bit tedious and frustrating. I mean, it's something that a lot of us probably saw in a first or second course in differential geometry. If you take the just R2, the regular plane, it has d by dx as a translation symmetry. If you now take the punctured plane and remove that one point, you still have a killing vector field, but it doesn't any longer generate a family of diffeomorphisms, because by any distance you might want to translate, there's going to be a point that gets translated to the origin and therefore out of the manifold. So you don't have a family of diffeomorphisms as you typically do on a compact manifold. You just have a local group of local diffeomorphisms, and so then you get sort of lots of tedious things with open sets and quantifiers and so forth. To try and make that a bit simpler, I've drawn the picture that's going to come up here. We have the R coordinate vertically, we have the Eddington-Finkelstein coordinate V and the angular coordinates omega. We're going to assume that we have an initial hypersurface h of y, which is the h of x, which is the graph over some set in the v omega parameters. So R on that initial hypersurface is given as a function of v and omega, and then you can go some distance further forward in R and backwards in R, and that gives you a slab. And we're going to have a so the big slab is U, and we'll have a sub-slab V, and then we're going to apply some sort of local diffeomorphism to V, and that's going to slightly shift it around within U. And similarly, we've got a slightly reduced set of initial data, H of Y, and it's going to get shifted around inside U, and then that's going to give us a slightly perturbed initial data set. All right, so we've got this slab, and we've got a sub-slab that we can move around a little bit with a small diffeomorphism and still stay within our set. So that's some sort of tedious set theory. All right. Okay, so our theorem is that if you have a background Kerr metric, you have the ingoing principal null vector, you have some slab and some sub-slab of it, and then you have the perturbed metric G that is within some Sobolev norm epsilon close on U to the background metric, then there is a diffeomorphism that one can make of that sub-slab V to a perturbed set phi V that remains inside the larger slab, and the pullback of the metric is now going to satisfy the radiation gauge. So we can impose the radiation gauge. We want to be looking at a perturbative theory, so we also have a second point that if you started out with something that was epsilon close, it's going to remain, order epsilon close, maybe 100 epsilon or whatever, but still order epsilon close. In terms of the trace condition, and this is where it sort of gets a bit funny, is that if you started out epsilon close, you can impose that the trace after applying the diffeomorphism vanishes not to order epsilon, but to order epsilon squared. And so then going to the linearization, this is why you can also impose the analog of the linear trace condition, that in the linearization, the trace is also vanishing. And also, once you're in this radiation gauge, finally, you get a symmetric hyperbolic system, and therefore it's well posed. So that's the main result. Any questions about that? All right. If not, let me race through the proof. I'm not sure I'm going to actually get to the linearization result itself, but we race through the proof. The proof is actually quite straightforward. The first thing to note is that if you had the radiation gauge imposed, then the vector field n, which is equal to minus partial r in the standard coordinates, is tangent to affinely parameterized null geodesics, not merely in the background, but also in the foreground. So that's one thing, is that these flow lines are null geodesics. And secondly, of somewhat less interest, on the initial data surface, you have the partial v tangent to it and the angular directions tangent to it, and you can calculate what the inner products of those vectors must be. And so then, from observing what consequences follow from the radiation gauge, if it were to hold, one can just sort of impose those by hand. So to construct the radiation gauge, you start out with the coordinates on the initial hypersurface. So that's just on the hypersurface. Then you construct on the hypersurface this vector field n so that it has the correct inner products that it should have coming off the hypersurface, and that it's future directed null. Then you just launch the null geodesics, and you take the coordinates in the space-time to be just constant along those null geodesics, and taking r as the affine parameter. I think this is quite similar in spirit to the part of the GCM construction in the Kleinman-Scheftel result, but there's more going on there that isn't the same. So the exact relationship isn't completely obvious to me, but there's certainly a close connection. So that's how we impose the radiation gauge. The well-posedness follows, with a bit of work, but it's not.
Peter, just so your conditions are on the initial data. So in that sense, it's differs quite a bit from the GCM.
I think there still might be some residual gauge freedom, and so if you use that residual gauge freedom at the beginning or at the end, that would still allow you to remain within the what we're calling the radiation gauge. So the difference might not be as large as it might initially appear.
Okay, no, I understand. I just wanted to clarify.
All right, so we use the GHP formalism with we need to specify a frame, so we can't use the background frame. We're using the frame of the metric G, not G ring. Whatever you use, the curvature components satisfy the Bianchi equations. This is 8 equations, which roughly speaking can be thought of as giving 5 hyperbolic equations, and for the 5 complex components, and 3 elliptic equations. So we just throw away the elliptic equations, keep the 5 hyperbolic equations. Then we need to construct the metric and connection. And we don't try and construct, as it were, the metric and connection directly. We try and, the variable for us is the difference between the background metric and the foreground metric, and the difference between the background metric and the background connection and the foreground connection. So as we'll also remember from our initial differential geometry course, Christoffel symbols, for example, or connections, aren't tensors. So that makes them difficult to deal with. But the difference between 2 connections is a tensor. And so then that makes it much easier to deal with. So by looking at these difference variables, we're roughly speaking looking at things that are tensorial. more precisely, in the language of GHP, which we use, it's got a property that's called properly weighted. And that allows it to be interpreted more clearly as a geometric quantity. So having got these quantities, the important property about them is that they all satisfy transport equations with respect to this n principal null vector direction. So we have the Bianchi equations giving us more or less the evolution for the curvature component, and then we have transport equations to recover all the other components. And surprisingly, there are no derivatives on the right-hand side of these transport equations. So that means we've got a symmetric hyperbolic system for the curvature components, the perturbed connection coefficients, the perturbed metric coefficients, and these distortion variables, which tell us how to set up the frame, the foreground frame. The proof of the ability to impose the trace condition is also fairly straightforward. Basically, what one does is apply the Price-Shankar weighting argument. They said that in the linearization, this quantity could be made to vanish. And so then when you do it at the nonlinear level, unsurprisingly, it vanishes to order epsilon squared. Although in hindsight, having looked at this, probably the radiation gauge is the more relevant thing. And we could have just treated this trace as a very small quantity to estimate as all the other quantities are being estimated.
Excuse me, Peter, I just wanted to let you know you've got about 10 minutes.
Great.
If you want to leave some time for questions.
Yeah. So I was going to have a slide on GHP scalars and what they are. But I think just in the interest of time, I'll skip over that and just briefly say what our linear stability result is. So we assume that there's some sort of energy bound and there's an integrated local energy decay estimate. So that's a basic energy and Morowitz estimate, which for simplicity we call a beam estimate. And these are known from previous works for the very slowly rotating case. But were someone to extend the range of A for which it was shown, our linear stability result would just carry through automatically. So in the de Fermat-Holzapfel-Rodniansky result, they got T⁻² decay for, let's say, energy type quantities using the de Fermat-Rodniansky RP estimate. There's refinements of that method developed by Angelopoulos, Arakakis, and Gayak that allow you to push that to more rapid pointwise decay. And so that was developed for the wave equation, the Angelopoulos, Arakakis, Gayak method. And we refined that further, taking advantage of certain properties of the Teukolsky equation. And so then we were able to get not just T⁻⁻1 decay that you might expect pointwise from the RP method, but quite a lot more rapid decay, which I'll describe a little bit later. So one obtains moderate decay in time for the +2 spin component and much more rapid decay for the spin -2 component. And basically, we're going to more or less reconstruct everything from the spin -2 component. All the metric components can be recovered from the spin -2 Teukolsky component by going through some of the connection coefficients that we recover along the way. So that allows us to recover all the metric coefficients. This is done by integrating along the transport equations. And there's sort of a hierarchy of transport equations. So you start with the Teukolsky variable, you integrate up to get one of the connection coefficients, you integrate that again to get one of the metric coefficients. Because we've got this complexified structure from GHP, we've only got 3 metric components to construct. So I've explained, start with Teukolsky, integrate once to get one connection coefficient, integrate again to get a metric coefficient, and then roughly speaking, integrate a third time to get another metric coefficient, and integrate a fourth time to get the final metric coefficient. So in doing this integration, if you know that you have rapid convergence to zero of the inhomogeneity, then that means you have convergence to a limit of the solution to the transport equation, but you don't know necessarily what that limiting value is. So the thing that we still need to do in the argument, as I've told you so far, is to show that those limits are all equal to zero. And this is where we use the Teukolsky Starobinski identities, which along null infinity can be written essentially as an elliptic angular operator to the fourth power on one of the components is equal to the time derivative to the fourth power on the other component. So integrating both sides of this equation once in time, we find that the integral of the quantity on the left is equal to the integral of the quantity on the right, but that is the integral of a time derivative. So it's just the endpoint values of the antiderivative, which is the third derivative in time of this psi2 component. So we can integrate that 4 times and still always get that the integral along null infinity is equal to 0, right? So we're integrating these transport equations, and we know that the integral from space-like infinity, the end of the initial data, along null infinity to time-like infinity, that integral has to be 0. And not only that, we can successively do this 4 times, which is exactly the 4 integrations that I described on the previous slide. So each of these, its predecessor decays rapidly to 0. That means it decays relatively quickly to a limit, and that limit is 0. And so that's how we get that all the metric coefficients are converging at a reasonable speed to 0 at time like infinity. So that's sort of the analysis that's done on null infinity, and we have an analysis that's sort of partly on null infinity and then partly in sort of the deep exterior, and then another analysis that's sort of somewhat closer to the event horizon.
In the deep exterior, don't you have to use a heat equation, sort of a parabolic equation, rather than transport equations?
No, for us, it's just transport equations.
So it completely kills angular part of the equation.
Yeah, that's right. Okay, so there's a subtlety here. Right, so there's the paper that we had in 2019, and then there's the paper that we had in 2021, where we looked at the nonlinear problem and its linearization. In doing the linearization, you can combine the linear quantities in different ways to get different linear variables. And so in the 2019 paper, we had chosen a sort of set of linearized variables. So it was, as you said, that there's time derivatives are equal to, time derivative of something is equal to an angular derivative of something else. And so then it does sort of have that heat type property that you were talking about, and we got quite a, like dozens of derivatives of loss as we descended this hierarchy. That the Teukolsky variable needed to be quite a lot more regular than the metric variable. In the more recent paper, particularly in setting up the well-posedness, we saw that there was sort of a slightly different way of combining the variables together so that you get just transport equations with 0th order terms on the right-hand side. Does that sort of make sense? Does that answer your question?
No, it's interesting. Yeah, no, I don't have an experience of that. I mean, for us, it was a parabolic equation. We get parabolic equations that we have to solve when we do
and was that really parabolic for you? Like first order in time equals second order in angular?
Yeah. Yeah, something like that, even false or the.
Oh, I see. Okay.
Yeah, sorry, I don't want to interrupt you.
All right, so that brings me to the conclusion. We introduced this new radiation gauge that the difference of the foreground and background contracted on the principal null vector is equal to 0. This gauge can be imposed. If you wanted to, you could use the residual gauge transformation to get it so that it linearizes to the full 5 conditions of Chrzanowski, and that with the right choice of frame, this becomes a well-posed system. So that makes it a nice choice of gauge. And then in the linearization, assuming other people's work on the existence of basic energy and Morowitz estimates, then we can improve that to rapid decay for the Teukolsky variable. And I've written down the variable here. And then we can, from the Teukolsky variable, reconstruct the metric components, and they all decay as r to the -1 as you go out in the radial direction, and just a little bit short of t to the -3/2 in the time-like direction, say up level sets of r. And there's more detailed decay along null infinity. So that's where I'll leave it. I hope that gives you enough time, Martin.
Well, thank you very much, Peter, for a beautiful talk. So we have some raised hands, I believe.
I only see yours. Do you want to call on people and then I'll answer them maybe?
Yeah, I mean, well does anybody have questions? That's the first. Was that a raised hand, Sergio?
Yes, yeah.
Yeah, please go ahead.
Well, I just wanted to ask about the final estimate. So besides the losses that you get when you do the decay estimates because of the trap region, you don't get any other losses of derivatives? So that's what you mean by well-posed gauge condition? So in other words, the L2 estimates that you get,
right?
Have no losses of derivatives.
So to do the well-posedness, you would do that in a sublab space, and there's no losses there. It's just quite a clean, basic type of argument. But that local well-posedness is not really the same sort of argument as we would use to analyze the long time solution. So once we linearize, then we're looking at the global behavior. And if you have the Teukolsky variable in one regularity, then the metric components that we reconstruct with the argument that we currently have, there's several dozen derivatives that in sort of an L infinity sense, the metric is quite a bit lower regularity than the Teukolsky variables. And the different metric components are not living in the same regularity space, because our linear estimates are much more L infinity based rather than L2 based, right? So if you have a transport equation, you just integrate, dtu equals v, then the solution u is going to generally have one level of regularity lower than the source term v.
Yeah, but usually one makes renormalizations, which allows you to gain back the derivative.
Yeah, that'd be interesting to learn more about. Yeah, certainly we would like to make progress on the nonlinear problem. We'll need to think about those sorts of things. That'd be interesting to hear about.
Are there any other questions for Pieter?
it took me a couple minutes to set up my screen share and everything, so maybe handing over is the right thing at this point.
Yeah, okay, sure. All right, well, let's thank Peter again for a beautiful talk.